Let's now take a look at this confidence interval problem, or actually these two problems. First off, we have the mean is given to be 12.05 and the sample standard deviation is found to be 0.1. Find an 85% confidence interval for the mean fill weight. I'm going to do this two different ways, mostly to illustrate that there's really no big difference between these two different ways. The first way is by using the t-distribution, that the confidence interval has the form x bar plus t times the standard error s over square root of n. Okay, and so in this problem that'd be 12.05 plus or minus t. Okay, for the t distribution, let me draw the picture down here at the bottom. We need to figure out the value so that 85% of the area lies in the middle. And so that can be done in Excel by using t.inv.2t 0.15 with we have 100 boxes, so that means 99 degrees of freedom. And so we get the cutoff value of 1.4508. And same other side for negative. If you have Excel 2007, the command would be tinv 0.1599. tinv without the dots, the assumption is that the first number is the two-sided area, and so we again get 1.4508. So over here we get 1.4508 times s, which is 0.1, divided by the square root of 100. So 12.05 plus or minus the margin of error. So this is our t value here. And so the margin of error would be equal to a1 times 0.1 over the square root of 100, which works out to be 0.0145. So here we only have two significant digits here, so I'll write that the same way here, so 0.015. Now, yeah, but probably just to emphasize a point that I'm about to make in a little bit, I'll put three places, so 0.0145. Okay, so that's the 85% confidence interval. Now, the other way that this could have been done is by, instead of doing a t distribution, we replace t here by z. Because I have a decently large sample, I could have put z here instead of t using the bell curve. Now let's see what happens if I make that change. The critical value here would be a little bit different. Okay, so instead, if I had used the z distribution, the bell curve, I would have had norm s inv of 0.075. Now that's the number I would need, because if 85% of the area lies in the middle, that means that 7.5% lies in the left tail, and also 7.5% would lie in the right tail. And so the z value that I would get would be very close to that, 1.44 instead of 1.45. And so the margin of error that I would get using this number would be equal to, minus e1 times 0.1 divided by the square root of 100. So I would get 0.0144 instead of 0.145. So the only difference by replacing t with z is that the last digit here gets changed from a 5 to a 4, and which is even beyond the number of significant digits permitted by the data that's found in the problem here. So all this to say, it makes no practical difference to use a t-distribution or the bell curve for when the number of degrees of freedom is so large, like 99. Continuing the problem, find a 99% confidence interval for instead of an 85% confidence interval. So the picture will be a little bit different, and so the z value here will be different. If I have a 99% confidence interval, the picture would look like this. So I'd have a much wider range so that 99% of the area lies in the middle, and 0.005 would lie in this tail, and then 0.05 would lie in that tail. So the z value that I would get this time would be norm Sn, but let me use 0.995 this time, so that 99.5% of the area lies to the left, so that I get the right edge of the shaded region, the positive number, so 2.5758. So the number here would be 2.5758. So 2.5758 falls here. And so I get the margin of error of 12.05 plus or minus. The margin of error this time, I don't need the negative sign that I had before, so I'll get rid of that minus sign. I get a margin of error of 0.026, say. And to again confirm that it really doesn't matter if I use the t-distribution or the bell curve, if I had used t-inv over here with 0.01, then I would got basically the same thing, 0.026 to 3 decimal places. So this is an illustration to say that the bell curve is a very good approximation to the student's t-distribution if I have a large number of degrees of freedom.